Ah! Oh, that's hot. That's hot.
Hello, I am Flammy.
Stop! You violated the law!
Wheeler, we are in the end game now.
Mr. Euler, I do not feel so good.
朋友是一个坚韧不拔的纪录片，在香港这座城市的设置，主演钱德勒。
Good morning, fellow mathematicians! Welcome back to another video. It's kind of the last time this year that we are going to calculate something on this channel. And I want to thank you guys for all your support over this whole year. This right here is Mathvengers Eulergame. And you might have seen it in the introduction. Some people from last year are gone. This is like symbolically meant with the Thanos snap, that some people from last year do not participate anymore. From some people, I don't know if they can still bring in their submissions, etc. But for the most part, this thing right here is settled. And I'm so glad that so many people are participating. Matt Parker did it this year. Thank you, Matt Parker. Such an honor to have you here on this show. And yeah, we are going to dive right in. This is Mathvengers, Eulergame. Everyone has to say something about Euler in some way, so it really doesn't quite matter. No real rules here. And yeah, what else should I say? The first spot, number one spot, is going to take my good friend John because, well, he's doing such a great job on his channel, and subscribe to him. He's quite a small math channel, but he's doing such a fucking great job. Also subscribe to all the other people who participate here. Matt Parker, probably Andrew Dodson, whatsoever, please do so. And now I thank you guys for watching, and I'm wishing you guys a nice show. See ya.
Hey, check it out. It's Euler's equation. Let's prove it. No, not like that. Let's define the function f of x to be e to the ix. Now, maybe I don't know much about this, but I can say a couple of things. First of all, if I plug in 0, that's just e to the 0, so that's 1. And another thing I could say is that this should probably follow the chain rule. So we'll say that f prime of x is I e to the ix. Okay, cool. Well, then we can view this as a sort of differential equation. This satisfies the differential equation y prime equals I y. And it satisfies the initial value y of 0 equals 1. Now, by a little theorem called Picard-Lindelof, named after some dead guys, this theorem, when its conditions are met, just says that given a differential equation and an initial value of the solution, there is a unique solution. So if we can show that cosine x plus I sine x is also a solution to this differential equation and initial value, we win. Okay, well, let's see. Let's let g of x be cosine of x plus I sine of x. Okay, now first of all, let's handle the initial condition. G of 0, cosine of 0 is 1, sine of 0 is 0, so we have the initial condition that's met. Now let's take the derivative. Derivative of cosine is negative sine. Derivative of I sine x is I cosine x. Now, this negative is a negative 1, so I can write that as I squared sine of x plus I cosine of x. And we factor out an I, and that is indeed the function we started with. So that tells me that this function g of x also solves the same differential equation coupled with the initial value. Therefore, by Picard-Lindelof, these functions are the same. F of x equals g of x. And so we can say that e to the ix equals cosine of x plus I sine of x. So that's Euler's equation proven through differential equations using the Picard-Lindelof theorem. Now, a lot of you may be thinking that Picard-Lindelof is a pretty big result and it's kind of overkill to use it to prove Euler's equation. But you know, I say overkill can be pretty fun sometimes.
Euler's number is irrational. Euler proved it, so there is no debate. Euler's number is irrational, and it's about 2.718. Leonhard Euler was the first one to prove it, and he used the simple continued fraction expansion to do it. But we will do it now in another way, following a proof which was first introduced by Fourier. And the series 1 over n factorial will be our starting point as the definition of E, where n starts at 0 and goes to infinity. And now let us see what happens if there would be an integer p and a natural q such that E equals p over q. Okay, and since we've had all natural numbers in our series and not just a few, we must at some point find our q. Let's subtract everything up to this point, and if you do now multiply by the factorial of q, then right at the start you might already see q factorial over q must always be an integer, since you can cancel out q, and cancelling out is what we are gonna do with the rest of these fractions, because we can see the whole denominator will now always be contained inside the numerator. So we can say this cancels out and leaves an integer. Okay, and we can now conclude for the left hand side it must always be an integer. Alright. Euler's number is irrational. Euler proved it, so there is no debate. Euler's number is irrational, and it's about 2.718. And if we now take a look at the right hand side, we will again see factorials, which we have to divide, only this time the numerator factorial of q is contained in the denominator, which leaves you with 1 over a product. And there you can see this product just gets longer and longer. And if we observe every single factor is bigger than q, so every single factor must be at least 2, then we know if every time we only write 2, the denominators will have to get smaller. So you know the whole fraction has to be bigger right now, but for this series I'm just gonna show you how you can visually see what this has to be. Just take a half and a quarter and an eighth and see how it gets closer and closer to 1. So you know this series converges to 1. But didn't we show that our right hand side must be smaller, which is tough because we stay greater than 0 if we add positive stuff. But there clearly is no integer between 0 and 1. So this is the point at which we have 1, because this contradiction right here shows you why no matter which p and which q you would try, it can never work, and therefore we see E can't be rational, QED. Euler's number is irrational. Euler proved it, so there is no debate. Euler's number is irrational, and it's about 2.71828184590452353602874741 approximately.
By now I'm sure you've learned that the sum of the reciprocal of positive integers squared is equal to pi squared over 6. There's quite a few different ways to prove this, but here I'm going to focus on exactly how Euler himself figured this out. So let's get started. The first thing that Euler did was he wrote down the Taylor series for sine of x. Then, dividing both sides by x, we obtain the Taylor series for sine of x over x. Now, here's the part where Euler comes in. Euler used the fact that you can write any sufficiently nice function as a product of polynomials with the same roots as the original function. So, for sine of x, we have roots at x equals 0, plus or minus pi, 2 pi, and so on. Now, this fact actually has a name. It's called the Weierstrass factorization theorem. You might be wondering why Weierstrass himself didn't use this to solve the Basel problem. Well, that's because Weierstrass factorization theorem wouldn't be proven until about 100
years later.
Because Euler is Euler. So, dividing both sides by x, we obtain an infinite product for sine of x over x. We can then expand this infinite product, term by term, collecting the various powers of x. For reasons we'll see in a second, we're just going to focus on the term in our expansion that's quadratic in x. We can then set the coefficient on this term equal to the x squared coefficient in our series expansion, which is 1/3 factorial, or 6. Multiplying both sides by pi squared, and Euler, have solved the Basel problem.
Hey everyone, in today's video I want to provide an introduction to calculus of variations, and show how we derive the Euler-Lagrange equation, and hopefully give some visual intuition for it. But we need to start with something that you might find a bit more familiar: optimizing single variable functions. From single variable calculus, you may recall how we find the local maxima and minima of functions. Given some function, f of x, a local minimum or maximum can occur at any point where the slope of its tangent line, df dx, is equal to 0. This should make intuitive sense, since we're just saying that a step in any direction will basically take you nowhere. This is a very key idea. At a local minimum or maximum, any small change in your input to the function will return a value further away in the same direction from your previous output. In calculus of variations, we're not concerned with finding fixed points of functions, but rather fixed points of functionals. The types of functions we had just looked at had a very specific set of properties. They had a domain and range of the real numbers. Essentially, you can kind of think of these functions like a machine. You put a real number in, and you get a real number out. Functionals are a little different though. With functionals, you input a function and get a real number out. To help distinguish between functions and functionals, we typically put their inputs around square brackets as opposed to parentheses. There's a crucial change happening here, and I hope you don't miss it. Since a functional takes a function as an input, our value can depend on any function of x, y, and its derivatives. More information is fundamentally encoded in it. We're going to spend the remainder of this video looking at a specific form of functional. J of y of x equals the integral of f of x, y, and y prime dx. If we're given a curve y, f just becomes a function in terms of x, and when we integrate over it, we're essentially summing all of its values over the curve y of x. While this may seem a little pointless now, it ends up being a very important idea. Now that you've gotten a sense for functionals, let's take a look at the central problem of the calculus of variations. For 2 points, a, x0, y0, and b, x1, y1, there are an infinite number of curves that pass through them. What we want to do is find the curve that is the stationary point of j of y. Fundamentally, we're finding a curve between a and b that minimizes the integral of f over it. We're going to solve this in a similar way to how we solved the one-dimensional problem. We're going to consider what happens when we add a small change to our input, but in this case, any small change to our input would be a function. Let's say that y is an extremal of j of y. We let y bar equal y plus epsilon times eta of x. Here, epsilon times eta is the small change in the function. To ensure that y bar still fits our boundary conditions, we need to let eta of x0 equal eta of x1 equals 0. Notice that j of y bar is now just a function of epsilon, j of epsilon. Since epsilon equals 0 is an extremal of j, we know that j prime of epsilon at epsilon equals 0 equals 0. Let's pay attention to simplifying dj d epsilon. From Leibniz's rule, we can rewrite this as the integral of partial f partial epsilon from x0 to x1 dx. Using the multivariable chain rule, partial f partial epsilon becomes partial f partial y bar times partial y bar partial epsilon plus partial f partial y bar prime times partial y bar prime partial epsilon. Referring back to our definition of y bar, we can simplify this again as partial f partial y bar times eta plus partial f partial y bar prime times eta prime. I now want to draw your attention to this term, partial f partial y bar prime times eta prime. We can use integration by parts to break up this integral even further. We let u equal partial f partial y bar prime, and dv equal eta prime dx. Then, du equals d on dx of partial f partial y bar prime, and v equals the integral of eta prime, which is just eta. By the rules of integration by parts, we can then rewrite this integral as partial f partial y bar prime times eta from x0 to x1 minus the integral of eta times d on dx of partial f partial y bar prime dx from x0 to x1. Notice that the first term becomes 0 since eta of x0 and eta of x1 both equal 0. If we plug this back into our original integral and factor out the eta in both terms, we get the integral of partial f partial y bar minus d on dx partial f partial y bar prime times eta. For our integral to be equal to 0 generally, we need this term to be equal to 0. This leaves us with the Euler-Lagrange equation. It is arguably one of the most important equations ever, and it completely revolutionized mathematics and physics.
Next up is me, the papa. This head seriously sucks. We are going to do something Euler now. Who would have thought that we are going to do something regarding Euler now? It's called the so-called Euler product, and I would like to present you this beauty, this major result in analytic number theory, using the Riemann zeta function. Okay? So, Riemann zeta function, you know the drill, ugly zeta as always of S is nothing other than the summation reciprocal of all the naturals added together to the S power, meaning it's 1 over 1 to the S power plus 1 over 2 to the S power plus 1 over 3 to the S power plus da da da, up until somewhere, infinity, okay? And Riemann zeta converges for the real part of S being strictly greater than 1, okay? This is for what it converges. If you put 1 into here, well, you are just going to get infinity, or you have to analytically continue this bitch boy. Now, we would like to turn this into an infinite product, and it's going to be something really surprising. I haven't done a video on that. Up until now, we are going to go the intuitive route just because the abstract stuff is kind of hard to understand. It involves a lot of estimations, etc. We're going to go the intuitive way here. So, I would like to multiply Riemann zeta function by 1 over 2 to the S power. Please note that 2 is the first prime number. Okay, has something to do with prime numbers, okay, analytic number theory, distribution of primes, yeah. Okay, so 1 over 2 to the S power, Riemann zeta of S, is thus nothing other than, so if you have 1 over B to the S power times 1 over A to the S power, this is 1 over A times B to the S power. Meaning we can just distribute the 2 into everything, so we get 4 to the S power, 6 to the S power, etc. So 1 over 2 to the S power plus 1 over 4 to the S power plus 1 over 6 to the S power plus 1 over 8 to the S power plus da 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 up until infinity. You might see something. Those down here are all the even numbers. Okay, it does make sense. If you multiply some number by 2, it's going to give you the even numbers. And since we have all naturals here, it's going to give you all the natural numbers, the even natural numbers in this case. Now we are going to subtract this thing from this thing. So zeta of S minus 1 over 2 to the S power zeta of S. Zeta of S is a common factor, leaving us with 1 minus 1 over 2 to the S power zeta of S. Sperm of S is thus. Okay, 1 over 1 to the S power is going to be preserved. Then we're going to get rid of this thing. 1 over 3 to the S power is going to be preserved. Plus, okay, 1 over 4 to the S power is going to cancel out, but then we have 1 over 5 to the S power plus 1 over 7 to the S power plus da 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 up until infinity. All the even things are going to cancel out. You might recognize this as something. We are going to continue this process. We are going to multiply this thing by 1 over 3 to the S power, the second prime number. So 1 over 3 to the S power times 1 minus 1 over 2 to the S power times zeta of S is thus nothing other. All of those multiplied with 1 over 3 to the S power. 1 over, this is going to give us 3 to the S power, plus 1 over 9 to the S power, plus 1 over 15 to the S power, plus da da da, up until infinity. And now, you might already see where we are going to go. Now, we are going to subtract this from this. We are going to have this part, so the first prime number captured, as a common factor, meaning we can factor it out on both of those, leaving us with 1 minus 1 over 3 to the S power times 1 minus 1 over 2 to the S power zeta of S. It's going to give us, okay, this and that is going to cancel out. We're going to get 1 over 1 to the S power. This and the 9 that we are going to get are going to cancel out. So 1 over 5 to the S power plus 1 over 7 to the S power. Then we are going to have 1 over 11 to the s power, and so on. A lot of stuff is going to cancel out. This has a certain name. This, what we are doing here, is basically nothing other than a prime number sieve. We are going to sieve out all the prime numbers, one after another. And do you see one thing? 1 over 1 to the s power is nothing other than 1. What happens if we are going to sieve out infinitely many, all the prime numbers that there are? Well, at the end, if we repeat this process infinitely many times, we are just going to end up with 1. We are going to sieve out all the prime numbers one after another. So we are going to get rid of all the composite numbers, just leaving us with the prime numbers. So 1 over 5 to the s power is the next one. Multiply it by this, subtract it by this thing then, and yeah, you are going to get rid of all the factors that have 5 in it. We are going to continue this process infinitely many times. Like I said, this can be made serious, this process, okay? This is nothing kind of hand wavy. It's an intuitive thing. The only thing you need to take care of is the convergence stuff. So we are going to have infinitely many factors right here. Then somewhere in the middle we have 1 over p to the s power. This is just some prime number, okay? Up until 1 minus 1 over 2 to the s power times zeta of s is thus 1 over 1 to the s power is just 1. Now, here comes the fun part. This thing right here is simply an infinite product over all the prime numbers. So this thing right here is going to be an infinity grill, okay, where p is prime. So our running index goes over all the prime numbers 2, 3, 5, 7, 11, blah, 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 times, okay, we have 1 minus 1 over p to the s power. This is our running index. That's why I wrote everything out. Zeta of s being equal to 1. And now under the condition that everything converges, drag the limit to the outside, blah, 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 divide both sides by this part, and then, yeah, you can collect all the terms yet again, meaning zeta of s is thus nothing other than the product of the reciprocal of all of those. P is prime, and we have 1 minus p to the negative s power to the negative 1 power. And this is the Euler product of the Riemann zeta function. One cool thing, the Riemann zeta function is the Dirichlet L series with a unique Dirichlet character modulo 1. What this is going to mean, we are going to see at the end of the video. I'm going to do one more. We are going to calculate an amazing infinite double product, basically, to calculate our boy pi, okay? Even though we can't have free blue and brown in here this time, we still can do something with a pi creature. One thing I want you guys to notice is that we can, in a certain region R, express each and every converging Dirichlet L series, so with a Dirichlet character here. Okay, it's going to look like this, just like the Riemann zeta function. G of k over k to the s power as an Euler product. Okay, this is the point right here, where it runs over all the primes. I'm not going to make a proof on that, it's quite complicated, okay? So 1 minus here of p over p to the s power to the negative 1 power. You can express each and every Dirichlet L series like this. We're going to need this at the end. I hope you did enjoy my submission, and now for the next one, woo!
What's going on, smart people? My experimental nuclear physics professor always liked to say that infinities only exist in the minds of theorists and you don't actually measure them. So it's problematic that in quantum field theory you get divergent integrals and infinities from the simplest of processes. Thankfully, there is a way of systematically removing these infinities through the process of regularization and renormalization. So for my part, I'm going to show you a training wheels version of this that just highlights the thought process behind renormalization. Then I'll show you it in the context of actual field theory. And finally, we will betray Euler. Here we have the first integral that we've ever learned how to evaluate in first semester calculus, where it's just power rule. The integral of x to the n with respect to x, 1 over n plus 1, x to the n plus 1, and we can't forget our constant c. And we can use power rule so long as n doesn't equal minus 1. That gives us 1 over 0. If n equals minus 1, we just remember that it's the natural logarithm for some reason. What I'm going to be suggesting is that you actually still can use power rule for n equals minus 1. You just have to contradict yourself a little bit and be careful and choose c such that it also diverges to counteract this 1 over 0 that you get for the 1 over n plus 1. So what I mean with this is if we choose c equal to minus 1 over n plus 1, and we eventually let n go back to minus 1, Then if we substitute this into the integral, we have I sub n equal to this common factor pulled out, x to the n plus 1 minus 1. Now what kind of witchcraft did I just do? Well, let's see what happens with this. What you're seeing now is a plot of the actual natural logarithm in blue, and then we're also plotting this function out for different values of n. And as we can see, as we let n get closer and closer to minus 1, this integral actually converges to the natural logarithm. So in introducing this diverging, what's called a counter term, we've removed the divergence in the actual integral and recovered the finite, the well-behaved function, the natural logarithm. So this is the same thought process that goes on in renormalization. Sure, we're dealing with more complicated infinite series and integrals than this, but it's exactly the same concept where we want to systematically remove the infinity so that we can get a finite result at the end. Now in quantum field theory, which is often done in d dimensions, typical integrals that you do produce gamma functions, and gamma functions have poles, which are characterized by this 2 over epsilon, which is in terms of the dimensionality of the problem. When d equals 4, this blows up. And then we have an additional term, the Euler-Macaroni constant, and other terms as well. And just as in the previous example, we learned that we can subtract the infinities and end up with a finite result, there's a renormalization scheme known as minimal subtraction, where you just subtract the divergent term. We get rid of this 2 over epsilon. But what happens to the Euler-Macaroni constant? Well, as it turns out, it's kind of useless, though it shows up in these integrals all of the time. When it comes to calculating actual observables in physics, it always cancels. So there's what's known as the modified minimal subtraction scheme, or MS bar, where we also get rid of the Euler-Macaroni constant, the 4 pi, and add an additional mass term to make this dimensionless. So in quantum field theory, you're dealing with people who subtract infinities on the regular, dimensional regularization, and the Euler-Macaroni constant just becomes collateral damage. But we still love E.
Hello, it's me, Matt Parker from Stand Up Maths and Numberphile. For this year's Mathvengers Euler's game, I'm going to calculate Euler's constant, and I'm going to use the identity that it equals the sum of the reciprocals of the factorials. So if I just add all of these terms together, or at least enough of them until I get bored, I'll get E. I'm going to do them by hand, which isn't so bad because I just work out the first one, then I divide that by 1 to get the next one, divide that one by 2, divide that one by 3, and so on. Today I'm actually in working at the Royal Institution here in London. This year the Christmas lectures are on mathematics, so whenever I get a break from working, I'll calculate a few more terms of my identity of E. So there you are. I got E to be 2.718 stuff, and the correct value of E is 2.718 stuff. That's pretty good. So in a pinch, if you need Euler's number, you can just use the first 7 terms of the sum of the reciprocals of the factorials. If anyone would like this piece of paper, I'll put it on eBay and all the money will go to charity. So there you are. That is Mathvenger Matt Parker out.
Hi everyone, Tibby's here. I'm hoping that someone else has already covered E, Euler's number. And if we display e to the x in Cartesian coordinates, we get this graph. But if we put it in a polar coordinate system, we get a logarithmic spiral. The logarithmic spiral can be constructed from equally spaced rays by starting at a point along one ray and drawing a right angle to a neighbouring ray. As the number of rays approaches infinity, the shape approaches the smooth spiral. The equation of the logarithmic spiral is r equals ae to the b theta, where r is the distance from the origin, theta is the angle from the x-axis, and a and b are constants. The logarithmic spiral was first studied by Descartes and Jacob Bernoulli. It is a pattern that appears in many places in the natural world. Jacob Bernoulli was so fascinated by the spiral that he wanted one engraved on his tombstone, but by error, an Archimedean spiral was placed there instead. So let's tie this back to Euler. Another member of the Bernoulli family, Johann Bernoulli, Jacob's brother, was an important influence on young Leonhard Euler, giving him weekly math lessons in his youth and recognizing his talent. So, Merry Christmas and Happy New Year, and get prepared for at least one person you know to send you this picture right here.
Most unsolved problems in math I can't understand. However, this one pretty much anyone can understand, and it's got the name Euler in it, so it's cool. Now, what we have here is a brick, a rectangular prism, and I've labeled all the side lengths A, B, and C, and I've also labeled all the diagonals X, Y, and Z, or the diagonals of the faces. Now, what makes this brick an Euler brick is if all of these values are integers. However, finding integers that makes this work is not easy. For example, if we were to try like 3, 4, and 5 for the side lengths, well, that's fine here. 3 and 4 have a diagonal of 5. That works. That's an integer. But 3 and 5 yield a non-integer diagonal, so that doesn't work. Now, this is not the unsolved part, though, so the next question would be, what's an example of an Euler brick? What's the smallest Euler brick that exists? Give that some thought, but not really because it's going to take you a while. Just finding these first few integers is not easy, but I memorized them for this video. Here we have it, the first Euler brick. So the side lengths A, B, and C are 44, 117, and 240 respectively. And then if you do the Pythagorean theorem with each of those pairs, you get these numbers. So like 44 and 117 give you 125. You do it with 44 and 240, you get 244, and then these two give you 267. So we can keep going from there, but again, this is the first Euler brick. Now, the equations that represent this are called Diophantine equations, which are just polynomial equations that only have integer solutions. And in this case, those look like this. So we have 3 Pythagorean theorems, and any integer solutions to these equations yield an Euler brick. Now, the unsolved part of this comes in when we add a 4th diagonal, one that goes from the bottom left corner to the top right. I'll draw that in, and I'm just going to call that D. If you can find an A, B, and C such that everything here is an integer, you have found a perfect Euler brick. However, the question of does a perfect Euler brick exist is still unsolved. That's the part we don't know. It's actually a perfect Euler brick is unsolved. When we add in that 4th equation, which would be a squared plus b squared plus c squared equals d squared, the diagonal, then we don't know if there are integer solutions that satisfy these 4 equations.
However, through the use of computers and just number theory, we have found out a lot about the properties of these numbers if an Euler brick does exist. For example, just from the Wikipedia page, we know if a perfect Euler brick exists, the smallest edge must be greater than 5 times 10 to the 11th. We know one edge, 2 face diagonals, and the long diagonal would be odd. We have a bunch of divisibility rules, and so on. That's about it though. Solving just those 3 Diophantine equations is not meant for a quick video like this, so it wasn't much I even could go into depth on. But I love unsolved problems, and this was an easy one to talk about.
Hey math crazies, let's talk about Euler angles.
What are Euler angles?
Here we go again. And who is Euler anyway? A mathematician that lived during the 1700s? But aren't you a physicist? Yes, but there's lots of math is useful in physics. None of this matters. Where was I again? Right, Euler angles. Say we wanted to transform from one set of 3-dimensional Cartesian coordinates to another. The most useful transformation would involve a consistent set of rules. That's where Euler angles come in. They represent 3 separate rotations. First, we rotate around the z-axis, which gives us a new x-axis and a new y-axis. This new x-axis is sometimes called the line of nodes, for some reason. Second, we rotate around that new x-axis, which changes the y-axis and z-axis. Third, we rotate around the new z-axis, which changes the x and y-axes again. This gives us the orientation of the second set of coordinates. I know, that's not as clean as, say, one rotation, but it is consistent, and that's what we wanted. It makes writing out the rotation matrices really easy. One z-axis rotation, one x-axis rotation, then another z-axis rotation. As long as you do them in the correct order, you're good. Where do we actually use these? Oh, all over the place. You can attach a coordinate system to anything. Like maybe elliptical orbits, for example. In our own solar system, planets, asteroids, and comets orbit the sun, approximately. But it's not like all those orbits line up. They all have different orientations in 3-dimensional space. Even the 8 planets, which orbit roughly in the same plane, aren't perfectly in the same plane. You might have heard of orbital inclination, but there are actually 3 parameters that determine an orbit's orientation in 3D space. Inclination, the longitude of the ascending node, and the argument of the periapsis, which happen to just be the Euler angles. Surprise! I'm sure you remember from earlier that Euler angles represent a transformation, which means there should be 2 sets of coordinates. The second set is attached to the orbit, but we'll need a consistent reference to start from. And we're human, so of course that reference is us. The initial xy plane is the Earth's orbital plane. The initial x-axis is directed towards something called the first point of Aries, which was in the constellation Aries thousands of years ago, but has since drifted into Pisces. The x-axis is just the line where the equatorial plane intersects the orbital plane. That's it. All right, let's say you wanted to know the orientation of Pluto's orbit. Starting from our reference coordinates, you'd rotate first around the z-axis by an angle we call the longitude of the ascending node. You'd think they'd come up with less complicated names for these things. Next, we rotate around the new x-axis by an angle we call the inclination. And finally, we rotate around the new z-axis by the argument of the periapsis. The periapsis being the point of closest approach to the sun. Periapsis just means close arch. So there you have it, the orbit of Pluto perfectly oriented relative to Earth. All thanks to Euler angles. One z-axis rotation, one x-axis rotation, then another z-axis rotation. Piece of cake. As long as you do them in the correct order, you're good. And remember, it's okay to be a little crazy.
Leonhard Euler was one of the great polymaths of his time, and we could spend hours talking about how he contributed to math and science and even music without barely scratching the surface, including how he started using the symbol pi to represent the ratio of a circle's circumference to its diameter. While less known to the public than folks like Einstein or Newton, one of his greatest accomplishments was actually correcting Newton and his theory of light, and his work championing the wave theory of light helped lead us to a more modern understanding and set the stage for Einstein's theory of relativity and arguably quantum mechanics itself. I'd encourage you to learn more about him and his work. Euler was one of the greatest minds of the 18th century, and a fascinating fellow besides.
We are already at the end. Like I said in the beginning, I'm the substitute for free blue and brown. Even though we can't have the pi creature here, I can still involve pi in this whole thing, okay? Has something to do with Euler products yet again, Dirichlet L series Euler product, and we're going to dive right in. I want you guys to remember that I have proven in an improvised session, okay, this has been improvised, that pi over 4 is exactly this series right here. It's called the Leibniz series or something like this. Now we would like to turn this thing into a Dirichlet L series, or just simply a Dirichlet series in general. One thing you should notice is that our running index goes from 1 here on the Dirichlet series, but here we have 0. So we have to find ourselves a Dirichlet character here of n such that such a series is justified. Okay? Now, what could this character possibly be? It has to be alternating. It needs to represent -1 to the nth power. I want you guys to notice something. Now, our Dirichlet character consists of 3 parts. All we do is cover the odd integers down here, odd positive integers, meaning our Dirichlet character is exactly 0 on each and every even n. Because we do not have 1 over 2, for example, 1 over 4. We only have 1 over 1, 1 over 3, etc. So every time our Dirichlet series goes to 2, for example, it's going to be 0 because we do not have those parts in here. Now the other 2 cases are that we have 1 and -1. Now when should our Dirichlet character be equal to 1? Well, this is always when we have even exponents, basically, okay? Now, even exponents mean we have 1, okay, starting here, on each and every n, which is congruent to 1 modulo 4. I want you guys to notice that our 1, -1 and 0 is cyclic in 4, okay? It takes on 3 cycles. And then we are at 4 yet again, and this makes it modulo 4. Now, on the even ends, won't matter. So 2 modulo 4 doesn't matter, 4 modulo 4 also doesn't matter. Meaning the only part that's left is n being congruent to 3 modulo 4. Okay, that's kind of complicated. Just try thinking through it and then write out this thing right here, and you're going to see that it's indeed equal to this right here, okay? It's just what it is, okay? It's kind of easy actually. It's not too hard. Also, I want you guys to notice our s is exactly 1 right here. Meaning we can rewrite our pi over 4 as being nothing other than this Dirichlet series, where k or n whatsoever starts from 1 of our Dirichlet character of n over n. Okay, this is just pi over 4 rewritten using this Dirichlet character. I'm doing this quite slow because it's kind of hard for beginners to see where this does come from. Now we would like to make use of this property. We are going to turn it under the condition that everything converges in a certain region. It does, okay, it converges absolutely and uniformly, this thing right here. We can turn it into this Euler product, meaning pi over 4 is thus nothing other than our Euler product, where p is prime, of 1 minus here of p over p to the s power, but s is 1, to -1 power. And now we can distinguish between 3 states. Every time we have an even prime number, it's going to be 0. There's only 1 even prime number, 2, so it really doesn't quite matter. This right here is going to vanish on this one. It's just going to be 1 product times 1, okay? It's going to vanish, so we got rid of this. Then we have the state where all prime numbers 1, so prime numbers congruent 1 modulo 4 are indeed 1, and then we have all prime numbers congruent 3 modulo 4 are equal to -1. We're going to split this up into 2 products. So pi over 4 is thus nothing other than, on the one hand, we have all primes congruent 1 modulo 4, and our Dirichlet character becomes 1 on this one. So 1 minus 1 over p, 1 over pp to the negative 1th power, and then times the product. We are going to split this product up into the next one, where p is congruent 3 modulo 4. And this exactly makes our Dirichlet character go to negative 1. Negative 1 become positive 1. So 1 plus 1 over p to the negative 1th power. And now we are going to write it a little bit differently. So we have 1 minus 1 over p. Okay, this right here is a super particular sum, or I don't know what it's called, something like this. Then p over p, so we have p minus 1 over p to the negative 1th power, meaning taking the reciprocal of this thing gives us p over p minus 1. And kind of analogously here, we are going to be left with p over p plus 1. And now we can write out the first few terms such that you can see what our product kind of looks like. Okay, let us write out the first few prime numbers. The first few prime numbers are, okay, 2 doesn't matter, okay, in our constellation. So we have 3, we have 5, we have 7, we have 11, we have 13, and so on. Meaning 3 is 3 modulo 4, okay? Meaning we are going to get 3 over 4. Then 5 is 1 modulo 4, so 5 over 4 times 5 over 4. 7 is 1, it's 3 modulo 4, meaning it's going to give us 7 over 8. Next one, 11 is 3 modulo 4, it's going to give us 11 over 12. And 13 is 1 modulo 4, is going to give us 13 over 12, and so on. And now you can get yourself pi by itself if you multiply both sides by 4, meaning pi is nothing other than this 4 and this 4 is going to cancel out. 3 times, okay, 3, hey, this is cool. So this thing right here, this tail is a bit more than 1, basically. Then 5 over 4, so that's the times, 7 over 8, 11 over 12, 13 over 12, and so on, until infinity. And this concludes Mathvengers, Euler's game. What else is there to say? There's nothing more to say, basically. I hope you did enjoy this video. If you did, please like and subscribe to everyone here. Once again, I would like to thank each and every one of you for bringing growth to this channel, for just making my YouTube experience also your YouTube experience, for just staying with me over the course of this whole year. We gained a lot of new Flammy members, and I'm so glad. I was working together with so many great people this year, and it's just such a blessing to be here on this platform. It's so much fun interacting with you guys, and I hope you are still going to support this channel right here, also in 2020. If you want to support this channel, you know how you can do so. And up until the next video, I'm wishing you guys Merry Christmas, Happy New Year, and also a flammable day. Ciao.
Hi there. Just a quick, flammable Merry Christmas and Happy New Year from Down Under. Wishing you many amazing maths adventures in 2020.
Merry Christmas and a Happy New Year.